Greg, you're the main introducer, I believe. You want to go ahead and introduce Samvit?
Sure, I'd be happy to. So Samvit has been working with me for, actually jointly advised by myself and Charles Menneveau on problems in wall-bounded turbulence flow. And he's going to tell you about some of what we've been up to for bringing ideas from superfluidity to classical turbulence. So Samvit.
Thank you for the introduction. So we'll jump straight in, and I want to start off by introducing our beloved Navier-Stokes with some extra forces added in. So you have the Navier-Stokes written out in this form, slightly different, but still the same. And you have a conservative force phi, and also a non-conservative force B. And so it was observed by Huggins in this rather well-written paper that this can also be written component-wise in this form, where we are using the usual Einstein index notation form. And this sigma jk is representing essentially these two terms, so this nonlinear term and this viscous term, and this gradient of h is representing this gradient here inside the parentheses. I hope you can see my cursor.
Yes.
And
Yes.
And yeah, so this is just another form of writing Navier-Stokes, where this sigma jk actually, which is again these two terms, it's representing the flux of vorticity. So in the so sigma ij is representing the flux of the ith component of vorticity in the jth direction. I hope I got that right. And so, which is clear if you look at the sort of the Helmholtz equation, the vorticity equation, and you have the same terms which you get in the vorticity equation, namely, so you have this advective term, then this is the vortex stretching and bending, which is so important for turbulence. You have this viscous dissipation, and then you also have this effect of the non-conservative Magnus force, which might possibly come from something like polymers in the flow. And the classical Josephson-Anderson relation is essentially the same as writing the Navier-Stokes out in this form. And if you take a time averaging, what that means is that this term, which represents the flux of vorticity, has to equal the averaged pressure drop. So it means if you have a flux of vorticity, you'll have a corresponding drop in H, which is total pressure, for example, or some sort of an enthalpy. And you get what is called this detailed Josephson-Anderson relation derived by Huggins for this case of a channel flow. So what you do here is you take the flow field and you split it into two parts. One is coming from this potential, and the other is the remaining part. So the important thing about this potential field is that it naturally satisfies the potential satisfies the Laplace equation. It's a scalar potential, and the inflow condition for this u phi is that it has to be equal to the full velocity field. So namely these first two conditions are satisfied. So at the inflow and at the outflow, u phi is equal to u, at least the component, the normal component of it. And then naturally you have no penetration at the walls. So what that means is that u omega at the boundary will be 0, because the normal component of u omega will be 0, and also that the two fields are orthogonal. So if you take a dot product of u omega and u phi, you see that it's 0. So what that allows us to do is to write the energy, kinetic energy, as the sum of the vertical energy and the potential energy, because the remaining part, which would be the dot of the two, is 0, because the two fields are orthogonal. And this is essentially what is the Kelvin minimum energy theorem, which is saying that with a given flux, E phi is like the base field, which is the least amount of energy, and then E omega is like a perturbation to it. And the Josephson-Anderson relation says that this potential field is sort of carrying the pressure drop, and there is a term T which is transferring sort of momentum or energy from the potential field to the vertical field. So you see that in this the equation for E phi, you have the term T acting like a sink if T is negative, and acting like a source for d omega dt, and where you also have the dissipation. So if you like, you can imagine that the energy which is being put into the channel through the pressure drop is being transferred to the vertical component through this term T, and then it's being dissipated away by the viscosity and the work of the Magnus force. And again, we can see that this term T is what we are going to be looking at some length, or something similar to T. And we also say that it's again related to the flux of vorticity, this Huggins flux tensor, which I talked about, which represents the flux of ith component of vorticity in the jth direction. And it equals, so this relation where H prime is, maybe you can call it the total pressure if you like. I'm sorry, this is supposed to be a phi. It's the potential. So this is representing the instantaneous equality between the energy transfer rate and the work done by the total pressure field. So you can think of T as the energy transfer rate. And this relation for channel flow, we thought, yeah, this is great. Let's just apply this to the channel flow. So we take the channel flow data from Johns Hopkins turbulence database, and we start off by calculating the U phi, which Huggins prescribes, with the condition that at the inflow, this potential field has to be equal to this full velocity field. So you can imagine this U in is taken from the database. It corresponds to a turbulent slice. But when we calculate the potential, we find that it's practically constant. So it's constant almost everywhere except for the ends. And so we thought, why not try to take U phi to be constant? So we make a slight variation of this. And originally Huggins derived this relation for superfluids where you don't have any vorticity coming in or you don't have any vorticity going out. Everything is generated inside, which is not the case for classical turbulent flow. So we tried this different potential, which is, you can say, simpler in some sense, that you still solve the Laplace equation, but with the boundary condition that this U phi is just equal to the bulk flow. So it's just constant. It's equal to bulk flow. And so it's bulk flow in. So U phi is basically constant in the whole domain. And we sort of get rid of these end effects, which we got. And we see that does the calculation go through? Well, it does, thankfully. So with this phi equal to U bar x and U phi equal to U bar, you still get the orthogonality of the two fields, and you still get that you have this T term, which is taking energy out of the potential and putting it into the vertical component, and then it's being dissipated by viscosity, as was the case for the original relation derived by Huggins. So, I forgot to mention that. So this relation has also, this form of the relation has also been derived for exterior flow in this paper by Professor Rank. And so we take this approach and we generalize it so that it's valid not just for this sort of a smooth channel, but also for this sort of a pressure-driven periodic channel, which is not just a smooth channel. So you can have some sort of roughness or variation as long as it's symmetric about this center, which is important. We can have the same sort of decomposition. The whole thing goes through essentially with the condition that this phi is constant at the inflow and at the outflow. So you can see that if you put x equal to minus L, phi is constant. If you put x equal to L over 2 or plus L, phi is constant. So we get the same decomposition, and we see that the whole relation goes through. And so coming back, so for this case, it means that if you have an average pressure gradient equal to gamma, then again you'll have these relations where you have this the vertical the potential part of the flow is taking energy in some sense due to this pressure drop, which is equal to gamma, and the T term is taking energy out of the potential part and it's putting it into the vertical part. So the whole thing goes through essentially in this new form. And we are interested then in this term T, which let's maybe think about this for a while. So you can see that this T term, again, acting as a sink here and a source here, since T is negative, we see that it has two components. The first, U cross omega, nonlinear part, and the second, which is from the viscous part. And for the case of the smooth channel, you see that, so this relation is always true. You can always write the left-hand side as the right-hand, as this right-hand side. For the case of the smooth channel, U phi is constant, as we had seen. So if you remember, you can see that U phi is constant. You see, U phi is just equal to U bar. And because of that, this term is 0 if you integrate it over the whole domain. And this viscous term is just equal to the sort of wall stress dotted with U phi, which is practically just the x component of the wall stress. So this is what is essentially balancing the pressure drop, if you like. And again, as I said, since U phi equal to U bar, this term goes to 0. And now we can look at the variation of the two terms averaged in wall parallel planes as a function of the distance from the wall. So we are looking at channel flow, the smooth channel flow at r eta of 1000, and we see that you have the nonlinear term acting against the drag. So in some sense, you can imagine this is sending vortices towards the wall. It's generating anti-drag, if you like, close to the wall, and the viscous term at y plus below, let's say 20 or y plus 10 is the one which is generating most of the drag. So this is just a zoomed in picture of this essentially. So you see that although the nonlinear term has the wrong sign very close to the wall, it's in most of the flow, in the bulk of the flow, it is what which dominates. And in time average sense, this red line of T should be equal to -1 in these units. That's because essentially you can think that the pressure drop has to be balanced by the shear stress. And we see that it's quite close. So this is not time average, this is instantaneous, but we still see that it is quite close, and it is entirely expected and has been derived in this paper in 2008, where we see that this should indeed be the case, especially in a time average sense. Now, what we are interested in further is the importance of is the role which vortices play in this transfer. So we want to see what are the vortices doing in the in this transfer, and we identify vortices in the standard way, which is, so we just use the lambda 2 criteria, so called, which is given in this famous paper, where you take the symmetric and anti-symmetric components of the velocity gradient tensor, you calculate another matrix A, which is S square plus lambda square, and you see the second eigenvalue, and that being negative implies the presence of a vortex. Alternatively, you can think that this being negative means that the velocity gradient tensor has a complex eigenvalue. So you can also think of it like that. Now we find that, for example, if we, so as I said, if lambda 2 is negative, that implies there is a vortex there. And we can choose how strong we want our vortex to be. So the more negative it is, the stronger it is. And if we reduce the magnitude, so if we say it's, for example, it's minus 0.25, you see more of these. So that's a less stringent criteria. And we see that, for example, for this criteria of taking lambda 2 to be equal to minus 0.5 in this channel flow, these vertical structures, even though overall they occupy only, I mean, a small section, maybe about 3-4% of the whole volume. They're responsible for 30% of the drag. So these very structures are responsible for 30% of the drag. And in this case, they have been colored by T, so the transfer. And as I said, the heights which we are at this point, the nonlinear term dominates. So you see that all these vortices have a sort of blue on their back and a red on their front. So let me play this out a bit more. You see that they are so you see that they are red at the front, and you did see they were blue at the back, but which means that, you know, T is negative at the front, which is sort of the correct sign for it, and it's positive in the leeward side of it. And you can see why that might be the case from this sketch. So imagine you have a vortex which is with vorticity into the plane, and you have local velocity going up and local velocity going down, and so u cross omega will point in, you know, minus x behind the sort of behind this vortex and plus x in front of it. And that's why roughly you can say that you'll have, you know, a positive in front of it, negative behind it, which is what we see. And so since I did mention that even though they occupy only a small portion of the domain, they are responsible for a lot of the drag. So I thought, okay, let us look at exactly how much they are contributing by doing some simple statistics. So what you see here for the 0.5 case, so the left side, the leftmost plot shows the conditional averaging. I'm sorry why I'm not quite sure why it's feeling pixelated here, but what you see is that if you just average over these structures, the magnitude of T which you get is very high, so it's really negative. Now remember, it's -1 overall, but if you just average over the vertical structures, you get this really negative, large negative contribution. And because they occupy such a small portion of the domain, their net contribution is small, but still you can say that they are punching way above their weight. So you can, you can relax the threshold for considering a vortex, and you can consider more and more of the vortices in the flow, and ultimately we see that they contribute the major share. So most of the sort of momentum transfer is coming from the vertical structures. This is a plot which shows the threshold for identifying a vortex on the x-axis, and the percent of T they contribute. So we were looking at -0.5. That contributes roughly 30%, maybe 34%, something like that. But for example, if you weaken the threshold a little bit and you look at this quantity, which is -1/8, it contributes about 62% of the drag, 60% of the drag, and occupies only 6% of the domain. So most of the drag is coming from these vertical structures, and this is that minus quarter, which is contributing 60% of the drag. So you can say that majority of the drag is coming from these structures, and you still see that effect where it's mostly red in the front and it's mostly blue at the back. Of course, subject to local variations. So now we can, since we see that our system sort of goes through, this is the proof which I'll skip over since we are short of time a little bit, and mention that similar parallel ideas have been explored in previous works as well by Chang in RSTA, and most recently by Menon and Mittal, where they employ a force partition method and also do something similar. So this phi is sort of like our phi, but it's different in the sense that the boundary conditions are very different. It doesn't correspond to a flow through, so it's designed for a sort of a different application, and we are still exploring how this interacts with what we have done. And I'd like to put up my conclusions and take any questions. Yeah, thank you. Oh, sorry.
Okay, any questions?
I might have a question. Yeah,
Go
can I
ahead.
ask it? Oh, so you mentioned the majority of the drugs from the vortex. So is that any kind of like coherent structure, like streaks or hairpin structure, or just in general vortex?
No, no. So you can think of it like a hairpin. So you do see hairpins. So for example, this will be an example of a hairpin. So this is a standard way of identifying a vortex. And the point is that these structures carry most of the transfer. They're responsible for the transfer between the potential and the vertical parts. So yeah, you can think of them as hairpins. Yeah.
Okay. Sure. Okay. Okay. Thanks. Yeah. Okay,
Sure.
So I guess the difference with what Menon and Rajat and Mustafa were doing, right, is that if you use their definition, then the force would be zero, right? Because theirs was,
right.
Let's say, for
That's right.
blocks
That's right.
on the flow, and then you identify the normal.
Yeah. So that's a different sort of
normal,
decomposition. That's right. That's right.
Yeah. So there's a question in the chat. Does this approach also work for channel flow with wall transpiration? It's an interesting question.
So I don't think so. It will not work with wall transpiration, I'm afraid. Yeah, because I mean, if we look at how why this works, if you ask the question why this works, it works because you have I guess this exact form might not work. You maybe, I'm sure it's possible to derive a form which will work with wall transpiration, but this precise form will not, because here you have same mass flux coming in and going out, which results in having u omega integrating out to zero. So you have so if you look at this this quantity, which is the inflow dotted with u omega and integrated toward an inflow plane, it's zero. So if you have wall transpiration, this might not be true. So I think this form won't work with wall transpiration, but I'm sure there might be a form which will. Yeah.
All right, very good. I think probably ready to go to the next talk. Thank you.
Yeah, thank you.
And the second speaker is Spencer Zimmerman. Spencer joined